guy is important. Okay, that's great. And now we apologize beforehand because it's going to be a disaster, but we would like to pick your brains how to find solutions to our problem. And, you can definitely help us. Only problem is going to be that we don't know how to explain it. We're looking at lattice problems in 1, 2, 3, 4 dimension, in practice 1 and 2. The reason why we are doing this is because we are trying to explain what chaotic or turbulent field theory is like. And the easiest field theory to do is a scalar field theory. So spacetime is discretized, and we actually work in Euclidean spacetime to make it easier.
Okay.
I mean, not always, but for purposes today, for the easy stuff.
Oh.
So what happens for field theory is that the easiest one is scalar field theory. And there are few versions, and the most popular in any literature on scalar field theories, 5 to the 4th field theory or quartic field theory. So this is essentially generalization of anharmonic oscillator to all of space. And the way the field theory works is that it's written in terms of action. Han, explain what's field theory and what are we trying to solve the problem?
Oh, okay. We have a defining equation that we have the field value on lattice, and there's a defining equation that needs to be satisfied. So to see if a lattice state like a lattice field configuration is admissible or not. So let's see. So we're able to write say action or Lagrangian of the system, and the defining equation is given by the derivative, the variational saddle point condition of the action, for example, like in this form. So this S of phi c is it's a action.
Do you have the expression of the action? What is this capital phi, and also what are those small phis?
Small phis are field value on each one of the lattice side, and this capital phi it's thinking the entire like array of field values.
So each small phi is a function defined scalar valued function defined on the lattice. Is that right?
The capital phi is a particular state.
So therefore, the small phi is not a mapping from the lattice to whatever states, space of states, but it's only defined on a site. Is that right?
Think of this state in this equation, number 7. That's a 5-dimensional vector space, if you wish, where a real space in 5 dimensions, where phi 0, phi 1 are different axes of it. And the point in that space is some set of values of these 5 numbers in reals to the 5. Does that help? In that 5-dimensional state space, a point is this capital phi. Yeah, phi is like a vector, and these guys are like components.
So basically, we have a scalar value. Here is just a scalar value on each one of the lattice side, which is a lowercase phi. Uppercase phi is for this figure, it's a 5-dimensional vector. Generally, it could be an infinite dimensional vector because there are infinite number of lattice sides on this integer lattice.
So for example, let's just take a look at small phi 0.
Yeah.
Is that a value or a function?
It's a value.
Okay, so phi 0 is the evaluation of the previously mentioned function at a particular site of the lattice.
Yes.
Okay, got it. Okay.
You can also think this subscript as, for example, for 1D lattice, it's like time. So it's like we can map the phi0 to phi1 using a map, but now we want to use a defining equation to describe this this lattice field. And sometimes we're able to write the defining equation as an action, and the defining equation is given by the variational settlement point condition. In quantum field theory, we can write the partition function of the state in.
You can just call it statistical mechanics. So Euclidean statistical mechanics.
So let me. Okay. So in field theory, at the continuous level, phi is really a field, meaning phi is a function on the space, and then you are integrating over all possible functions. It's just that each one has a weight.
Right.
And then now, because if I understood correctly, you discretize the space, and then this capital phi becomes essentially a vector, a very high dimensional and yet finite dimensional object. And then you do the usual stuff where you basically just integrate over each component of the vector, and then there is a so-called action functional S, which is really just a function that maps very high dimensional vectors to, say, real values.
Here, everything is real. Yeah.
Okay. Okay, great. Okay, got it.
Okay.
So, equation 3 tells you its probability. And equation 4 says exactly what you just said. Because you have discretized the space-time, then you're computing a product. Z is the name of lattice site. It could have 1, 2, 3, 4 discrete coordinates, integer. This Collier lattice says it's some kind of lattice, so it's easiest to first understand it on finite lattices before going to infinite lattice. The classical equations, just like in mechanics, are extrema of this action. So they are Euler-Lagrange equations in a discrete lattice form rather than continuum derivatives form. Shang-Chi's task is to actually find these solutions.
Find the solution to the Euler-Lagrange equation, or what's the solution to what? I'm sorry.
Euler-Lagrange equation. So all configurations on a lattice, which we call them lattice states. The solution. These are solutions that every place locally satisfy Euler-Lagrange.
Associated with the action S, correct?
Yeah.
Okay. Okay.
Now it's actually more general than mechanics, but it's kind of useful to this language because everybody is familiar with mechanical version of it.
Yes. So for quantum field theory, each state has its weight. It's deterministic. The field configuration can only exist if this condition is satisfied. So
this is the saddle point condition, the extremum of the action condition.
So just now I was trying to make sure whether the Euler-Lagrange equation is the one associated with S, and if it was, then I thought we want to solve for the stationarity condition, which is this right-hand side of equation 5, this other S, which is abuse the notation, but the other S being equal to 0. I thought this is the stationarity condition. But then
you're right.
But then what is this additional small f?
It's a functional derivative, right? So you're varying the action. It has to be satisfied on every lattice site. So you have to vary field on lattice site Z, right? The equation is true every place. In the usual mechanics, this is time, and it has to be satisfied for every time. But on lattice, it could be space-time. This M, you can ignore it for purposes of discussion.
If S plus phi M as the action, then this is a variation condition of the entire minus S5 plus 5 times I.
So the usual way to get correlations is statistical mechanics. This is just a linear response term. You take derivative, set m equal to 0, and that brings down the field, and you're computing expectation values of field and products of field called correlation functions. So that's why it's there. It's a standard thing in StatMech. Every lattice site has a little m associated with it. M on the site Z. It's like a source or
scalar value, which is called small m. Z is the label, it's a subscript, the position on the lattice. So basically we use this condition to find the solutions or admissible orbits. And now because this is deterministic, so the weight here is given by the Dirac delta function, because if this condition is not satisfied, then that's not a solution. That's allowed.
What is the role of equation 8?
Partition sum is sum of our probabilities. Each state has its probability. And this is a formula for probability for state phi C. At the moment, it's not terribly essential. We just want to solve Euler-Lagrange equations. This is why we need them.
So you want to solve for Euler-Lagrange equation. You have a function.
Few pages down, we actually have this equation. There is a lattice Laplace operator, and then, so if you get through 13 and 14, which Moulay knows, and then we show him what equation looks when you have a nonlinear term, it'll be much easier to understand.
So this box is a Laplacian, and mu square is a constant. If we compute the derivative of this action, we get the equation like 16, where
is the small m known? Is it given to you, or it's an unknown that you have to solve for? And then,
you're given m, and you have to find phi that satisfies that.
Sure.
One of the simplest problems with this equation 16.
And the parameter is this S, A, or G. It's a continuous number. So you set parameter to some value, and you have to find all the solutions for given lattice states. We're looking at Bravais cells, hypercubic lattice. Then we have to find all the solutions.
Okay, so for the simple case listed by equations 16 to 18, phi satisfies periodic boundary condition, and you want to find all solutions.
These are the problem we want to solve. So actually, when we solve them, we only use this equation, not using the action.
Are you asking me how to solve it?
We use a very crude and inelegant method to solve this in one-dimensional lattices. The way we think about how you solve these problems is you have on the lattice side, you have a potential function. You have some function. And it has what Laplacian does, it compares the lattice side to its neighbors. And you have solved the problem where on every side, what you get from your neighbors is exactly what you compute for a nonlinear potential. You're balancing kinetic and potential part. Laplacian is what is called kinetic in usual time evolution. When you look at these problems, you have to solve a problem where at every site you look at your two neighbors and you say, am I too big or am I too little? And Euler-Lagrange equation is the equation that solves that. So that's what we are solving. And you have infinitely smarter methods to do it. And we need to learn smarter methods because right now we've been just solving problem on very small one-dimensional lattices and very short ones. The real problem we want to solve is in higher dimensions. So we need much better methods than we have. I dragged you in here because but I've listened to all your seminars, so I know you can do it.
You actually want all the periodic solutions?
We know their number is finite. They're all unstable, hyperbolic, and we know how to count them, and we are good. But we know their number is finite for any finite Bravais cell on the hypercubic lattice. We have to find all of them up to certain period or multiple period. If you have multiply periodic domain that tiles the space-time. And they should be easy to find because they're not unstable. I mean, they're hyperbolic, but they're not exponentially exploding or anything when you look at global solutions. So that's number one. Number two, we have to compute the determinant. You get a Hessian when you study the local stability. The determinant of that Hessian is what showed up in that probability formula. So that its inverse is the probability of given states. So these are like two things we have to be very good in computing.